In this video, I just want to do a few examples of how to find Taylor polynomials of different degrees. We didn't do, in class, we explored more kind of the logic behind how would you construct a Taylor polynomial. Because one of the things about Taylor polynomials is, so for an nth degree Taylor polynomial, its first n derivatives agree with the function that it's approximating. For example, the first, if we called it, in the lab we called it g of x, right? We said that, so g of a equaled f of a, right? And then that g prime of a equals f prime of a, and that g double prime of a equals f double prime of a. And we use these facts to construct the nth degree polynomial, to find those coefficients that would work. In this case, remember, we were doing e to the x, all right? So what I'd like to do now is look at some applications. We ended up with this formula for Tn of x, where it was f of a plus f prime of a over 1 factorial x minus a plus f double prime of a over 2 factorial x minus a squared, plus we'd have the third derivative evaluated at a 3 factorial x minus a cubed, and we just go up to whatever the nth, the nth derivative evaluated at a over n factorial x minus a to the n. All right, and then the shorthand for this is that we say we could use this index of j equals 0 to n of the jth derivative evaluated at a over j factorial x minus a to the jth power. And I talked about that in the previous video, kind of what that means. So let's look at an example of how we might use this. Let's say we want to find t3 of x for natural log of x at centered at x equals 1. So this is our a value, all right? Here's our f of x, and we want to just plug into this formula. So if we're doing t3, we're going to go this far, all right? So we need these 4 terms, and the main thing that we're going to have to find here are these pieces: the f of a, the f prime of a, f double prime of a, right? The rest of this doesn't really change. We have to plug in, but it's always 1 factorial, which is 1. It's always 2 factorial, which is 2. It's always 3 factorial, which is 6. 4 factorial, which is 24, and so on. That part of the equation doesn't change. And then the a, whatever a is, we're just going to plug it in there. The fact that this is at the first power, second power, third power, that doesn't change. So really, most of the work in computing something like T3 is going to be finding these derivatives and evaluating them at whatever the value of a is, wherever we're centering, kind of starting at, right? So approximations near where we're starting will be good. The farther we get away from that point A where it's centered, as we saw in the lab, the farther you get away, it doesn't match up so well. Okay, so let's go ahead and do this. So ln is f, so f of 1, right, because that's our a value. That's natural log of 1, which is 0. All right, now the derivative of natural log is 1 over x, and f prime of 1 then is just going to be 1, right? 1 over 1 is 1. The second derivative, now if you think of this as x to the negative 1, you can do it that way, but you should get negative 1 over x squared. So the second derivative evaluated at 1 is going to be negative 1. And then the third derivative, all right, again, if you think of this as negative x to the negative 2, then using the power rule, we would get 2 over x cubed. So the third derivative evaluated at 1 is just 2. So we've got these things that I've circled. We've got these right here, 0, 1, negative 1, 2. So t3 of x, first we're going to have 0 plus 1 over 1 factorial x minus 1, because that's my a value, plus the second derivative evaluated, so that's negative 1 over 2 factorial x minus 1 squared, plus 2 over 3 factorial x minus a cubed. We can simplify this a bit. We don't need the 0. 1 divided by 1 factorial is 1, so we don't need that out front at all. We'll just rewrite that as x minus 1. And this is going to be minus rather than plus and negative. I'm just saying minus. 2 factorial is 2, so that's just 1/2 x minus 1 squared. And then this can be simplified. That's 3 factorial is 6, 2, 6. Whoops, why did I write a? That should be a 1. That should be a 1. That's cubed. All right, finally I could simplify this a little bit just to kind of make it look a little bit nicer. Minus x minus 1 squared over 2. And notice that 2/6 is 1/3, so I get x minus 1 cubed over 3. All right, so you can kind of see a nice pattern emerging here. X minus 1, and then x minus, and then there's a negative and a positive. I would venture to guess, if you look at the fourth derivative here, right? We don't need to do this, but I'm guessing it's going to be negative, right? Because this is like 2x to the negative 3. So when you multiply, we're going to get negative 6 over x to the 4. So that indeed would be negative. So we see this pattern, positive, negative, positive. This is to the first power, second power divided by 2, third power divided by 3. You know, we could go out on a limb here and say the next one would look like x minus 1, or minus x minus 1 to the 4th over 4. And actually, one of the problems you'll need to be able to do that, because it just asks you for a formula for Tn of x. So you'll have to try to look for a pattern that you can kind of summarize. So sometimes rewriting them like this makes it a little bit easier to do that. Okay, that's one. I just want to do one more example similar to something that is on the homework. So in this case, we're given that our function is e to the x. And what they want us to do is use T2 to estimate e to the x at x equals negative 0.5. And they want us to use T2 of x, or the second degree Taylor polynomial centered at a equals 0. All right. So the first thing we would need to do is to find T2. But we already did that in the lab, so I'm not going to repeat that. Remember, this is our second degree polynomial. We found that to be 1 plus x plus 1/2 x squared, if you recall from the lab. All right, so that's our T2 of x. And remember, we were also centered at 0. If we were centered at 1, this wouldn't be the same, right? This would be an x minus 1, and this would be an x minus 1 squared, and so on. But this is the second degree polynomial for e to the x centered at a equals 0. And what we'd like to do is we're going to estimate e to the negative 0.5 using the second degree Taylor polynomial, and then figure out what the error is. All right. So the first thing is to just plug this into our calculator, because in order to find the error, I need to, well, ultimately I'm going to do T2 of negative 0.5. I'm going to do both of these, and then I'll find the absolute value of the difference, right? This is the exact value. This is our approximation using the second degree Taylor polynomial. We'd like to know ultimately down here, we're going to look at the difference in absolute value. All right. So the first thing, we can just plug this into our calculator. I did have to round because I didn't want to write forever, but I get 0.60653. All right. And then here we can just plug this in for x, right? So I'm going to have 1 plus negative 0.5 plus 1/2 negative 0.5 squared. All right. Well, that's just, if I rewrite this with fractions, I'm going to have 1 minus 1/2 plus 1/2 times negative 1/2 squared. Well, this is just 1/2. 1/2 squared is 1/4. So this is 1/4 times 1/2. So it's 1/2 plus 1/8, right? Which is, well, so that's 4/8 plus 1/8. That's 5/8. which, as a decimal, gives us 0.625. So, it's not bad. It's not great, but it's not bad. Remember, this is only the second degree Taylor polynomial, so we wouldn't expect it to be too precise. Ultimately then here, if you just take the difference between these two and then take the absolute value, you'll find that the error was 0.01847. Okay, so those are just a couple of examples of the sorts of things that you'll have to do on the homework. I just want to kind of connect it to our work on the lab and give you some examples of how we would apply the results of the lab to some problems.